in the previous lecture, we have started to deal with the four fundamental interactions. We have seen actually these fundamental interactions are gravitational interaction, electromagnetic interaction, weak interaction, and a strong nuclear interaction. In fact, in that introductory lecture, we have seen the important basic fundamentals of all these four fundamental interactions. And at the same time, we have also discussed in some extent in detail regarding the gravitational interaction. And as I have told you earlier in that lecture, that in the forthcoming lecture, we will discuss separately all these remaining three interactions, that is electromagnetic interaction, weak interaction, and a strong interaction. So today we are going to discuss the important features or important facts regarding the electromagnetic interaction, and then in next lecture we will see in detail the concept of a strong interaction and the weak interaction. But in this lecture, this will be just a short lecture, we will see only the concept of electromagnetic interaction. You know, the word electromagnetic refers both electricity and magnetism. In fact, before the advent of electromagnetic induction by Faraday and the electromagnetic theory proposed by Maxwell, electricity and magnetism was thought of two different things. But at first, Maxwell unified the concept of electricity and magnetism. Actually, according to Faraday's law of electromagnetic induction or Maxwell's electromagnetic theory, if an electric charge is in motion and it produces a time-dependent electric field, then that time-dependent electric field actually produces a magnetic field which varies with time and space periodically. In the similar manner, a magnetic field which is time dependent, that produces electric field, and that electric field actually varies with time and space periodically. So we cannot think these two things are different, but the electricity and magnetism are actually a same thing, and actually it depends on the state of motion of the charge. Actually, electric and magnetic field both are produced by electric charge, that depends on the state of motion. Okay, and so you can say that I have mentioned here that the term electromagnetism is because the electricity and magnetism are both part of the same phenomenon. Okay. And as I have told you that this electromagnetic interaction depends on the nature of the charge, magnitude of the charge, and the state of motion of the charges between which this interaction takes place. Okay? And actually, when we consider that the two charges are at rest, and two charges means 2 point charges. If you consider two charged particles, let us consider first one is Q1 and another is Q2. And both point charges are separated by a distance r, and these 2 point charges are at rest. Actually, in this condition, there is only electric interaction between these 2 point charges, and that interaction is actually called Colombian interaction. And this is actually the simplest form of this interaction when we consider that the interacting charges are at rest. And in this condition, you know, we have definitely studied the Coulomb's law that the force acting between 2 point charges Q1 and Q2 at rest separated by a distance r is given by this simple formula: F equal to 1 over 4 pi epsilon naught Q1 Q2 over R square. And you know, actually this is actually the magnitude of the electric force acting between these two point charges. In fact, this electric force may be attractive or repulsive. It depends on the sign of the charges. You know that if the 2 point charges are of similar signs, it means if this Q1 is positive and Q2 is also positive, then repulsive force acts between them. Similarly, if Q1 and Q2 both are negative, then again there is repulsive force between the 2 point charges. But if the sign of the charges are opposite, it means if Q1 is positive but Q2 is negative, or Q1 is negative and Q2 is positive, then this interaction is attractive. Okay. Now you can see from this formula, actually this force varies with distance r in just inverse of the square of r. So this is also known as inverse square law, you know. And from this formula you can see if r tends to infinity, it means the 2 point charges are infinitely separated. So if r will be infinity, you can see the formula F will tend to 0. So you can say that this force will vanish only when the interacting charges are at infinite separation. So this is just a long range force. This force even acts between 2 point charges when the charges are separated by a large distance. Even then this interaction takes place. So we simply say that the electromagnetic interaction is a long interaction. Okay. So it is a long range force, or it is a long interaction, you can say. Now, from this Coulomb's law, if we want to find the magnitude of the force acting between two protons separated by a distance r equal to 10 to the power minus 15 meter. Actually, you know, this 10 to the power minus 15 meter is just the size of your nucleus. This is just of the order of radius of a nucleus. Okay. So if you consider that the two protons are inside a nucleus, then we simply say that the separation between the two protons will be of the order of 10 to the power minus 15 meter. So what will be the strength of this Coulombian force acting between two protons inside the nucleus? You can easily find the numerical value of that force from Coulomb's law. If you consider that the force is Fe, E for electric word, and then 1 by 4 pi epsilon naught. The constant 1 over 4 pi epsilon naught, you definitely know this is 9 into 10 to the power 9. And as the two interacting particles are protons, so Q1 and Q2 both will be same, and that will be equal to charge of the proton. And you know, charge of proton is 1.6 into 10 to the power minus 19 Coulomb. So this will be this much square, and over r square, and we have assumed that r is equal to 10 to the power minus 15 meter. So I have substituted here 10 to the power minus 15 square. And after simplification, you will get that this Fe will be almost equal to 230 Newton. It means inside a nucleus, the Coulombian force acting between two protons is of the order of 230 Newton. Okay. Now, if you want to compare the strength of the gravitational force and the Coulombian force acting between the same 2-point masses or same 2-point charges, then let us find what will be the strength of the gravitational force acting between the same two protons. It means we are now going to find the magnitude of gravitational force between two protons inside a nucleus. So in this condition, you know, we will apply actually Newton's law of universal gravitation, And according to that law, the gravitational force between these two protons will be what? This will be G times m square over r square. Here m is actually mass of a proton, and since both of the particles are protons, so this will be m times m, that is m square. Okay. Now substitute the numerical values of all these quantities. You know, this universal gravitational constant G is equal to 6.67 into 10 to the power minus 11 Newton kg square per meter square. And m square, this is mass of the proton, and you know mass of proton is 1.67 into 10 to the power minus 27 kg. So that much square. And r we take 10 to the power minus 15 meter square. And after simplification you will get that this Fg is equal to 2 times 10 to the power minus 34 Newton. Now, the electrostatic force acting between two protons inside a nucleus is of the order of 230 Newton, and gravitational force acting between the same two protons is of the order of 2 into 10 to the power minus 34 Newton. So, let us compare the strength of these two forces. For this, let us find Fe over Fg. Fg, this is 230 Newton, and Fg is 2 into 10 to the power minus 34 Newton. So this is almost equal to 10 to the power 36. What does it mean? It means the strength of the gravitational force is much smaller than the electric force acting between the same two particles. Actually, this electric force or the electrostatic force or Coulombian force acting between these two protons is 10 to the power 36 times stronger, greater than gravitational force. So we simply say that this Fe is much greater than Fg. So if you want to find the interaction between two protons inside a nucleus, you can neglect the gravitational interaction between them. So in the previous lecture, I have told you, when you talk about the nuclear physics or the interaction between nucleons, then we neglect the gravitational force, neglect the gravitational interaction. Gravitational interaction is actually effective, it is considered, it is appreciable only when we talk about the large scale calculation. That is, if you want to find the gravitational force between the formation, for example, if you are dealing with the formation of stars, then you have to consider gravitational force. In fact, in the discussion of interaction between elementary particles, gravitational force almost plays no role. Okay. Now you know that any interaction according to the field concept is mediated by some particle, and definitely you will see that all these four interactions are mediated by bosons. The mediating particle of any interaction is definitely a boson. So this electromagnetic interaction is actually mediated by a boson which is called photon. Okay. In fact, you can say, in other words, that the field quanta of this electromagnetic interaction is a massless boson, and that massless boson is known as photon, and the spin of this photon is equal to 1. So when you say that electromagnetic interaction takes place between two charges, what actually happens there? Actually, if you consider that this is a charge Q1, this is a charge Q2, and electromagnetic interaction takes place between them. Actually, this interaction is mediated by a photon. In fact, one of the particles, let us say Q1, will shoot out a photon, and that photon will be absorbed by the another particle. And similarly, this Q2 will shoot out a photon, let us say this gamma photon, and that will be absorbed by Q1. So actually this electromagnetic interaction is just an exchange of photon. When you say that electromagnetic interaction is taking place between two particles, what does it mean? It means there is an exchange of photon between the interacting particles. So we simply say that the agent which actually causes this electromagnetic interaction is photon, which is a boson having a spin 1, or you can say h bar, and its rest mass is 0. Since its rest mass is 0, you know from a special theory of relativity that if rest mass of a particle is 0, definitely the speed of particle is equal to a speed of light in free space. So this mediating particle photon will move with a speed equal to c, that is a speed of light in free space. Okay. Now you know that any interaction, the strength of any interaction is determined in terms of a dimensionless quantity which is called actually coupling constant. For every interaction we define a coupling constant, and this coupling constant is a dimensionless quantity. Okay. So this in case of this electromagnetic interaction, the coupling constant is a dimensionless number. It is just a dimensionless quantity, and that quantity is actually called fine structure constant, and that is denoted by the symbol alpha. Actually, when I was teaching you the atomic and molecular physics, then in case of hydrogen spectra, I have discussed this fine structure constant, and that fine structure constant you have seen in that lecture that it is defined as E square over 4 pi epsilon naught h bar c. In fact, this E is charge of an electron or a proton, and when you will substitute the values of all these quantities, then you will see that the value of alpha will be almost equal to 1 over 137. This is just this is just an approximate value. There will be 137 point something, but this is almost equal to 1 over 137. This is called fine structure constant, and this fine structure constant is actually the coupling constant for the electromagnetic interaction. Okay. Now you have seen that this electromagnetic interaction takes place between the charged particles, and so you can say that this electromagnetic interaction is charge dependent. But at the same time, this interaction also depends on the third component T3, or you can say the Z component of the isobaric spin. So you should remember that electromagnetic interaction depends on charge and on what? The another factor on which this electromagnetic interaction depends is actually the Z component or the third component of the isobaric spin. When you say Z component of isobaric spin, you denote it by the symbol Tz, and if you say that this is third component of isobaric spin, the appropriate symbol will be T3. Actually, when electromagnetic interaction takes place, the iso spin does not remain conserved. In fact, all those processes in which the change in iso spin is either equal to 0 or equal to plus minus 1, all those processes are governed by the electromagnetic interaction. So this is actually the selection rule, or you can say that during EM interaction, iso spin will not remain conserved, but there will be a change in the iso spin, and that change will be actually equal to either 0 or plus minus 1. When you say that change is 0, what does it mean? It means that there will be no change in isospin, but this change may be plus 1. It means the isospin may be increased by 1 or may be decreased by 1. So remember it. In fact, in the forthcoming lecture, when we will see the different conservation laws, then we will actually discuss the conservation of isospin, and then this fact will be discussed in very detail. But here I am just going, our aim is just to know all the important facts regarding the electromagnetic interaction. So I have mentioned this fact here, that isospin does not remain conserved in the electromagnetic interaction, and this electromagnetic interaction is governed by this isospin rule, that if the EM interaction will take place, the change in isospin delta T will be either 0 or plus 1 or minus 1. Okay. But except this isospin, other quantum numbers remain conserved during electromagnetic interaction. In fact, this thing will be discussed in very detail in the forthcoming lecture, as I have told you, when we will discuss actually the different conservation laws for different quantum numbers. So you can say that the other quantities or other quantum numbers, you can also say, like charge, baryon number B, lepton number L, hypercharge Y, parity pi, strangeness S. All these quantities or quantum numbers remain conserved during EM interaction. You should remember. But we will explain this fact in the forthcoming lecture in very detail. Okay. Here I have just given you just an information, because if a question will be asked regarding the 4 interactions, then in dealing with this electromagnetic interaction, you have to mention this fact. Okay. Now, after knowing all these important facts regarding the electromagnetic interaction, we will now see some of the important examples of this electromagnetic interaction. Okay. So I have mentioned here some important applications in which electromagnetic interaction takes place. So the first, as a first example, here I am taking that the capture of a photon by a proton. When a proton captures a photon, then there is actually two possibilities, two phenomena takes place. Due to the capture of photon by a proton, actually mesons and hyperons are produced. You can see this reaction. See this reaction. This is your photon gamma, and this is captured by the proton. So in one mode of interaction, after capturing of this photon by the proton, we get this meson, pi 0 meson. This is also called neutral pion, and this is your proton. And in another mode, after capturing of this photon by this proton, we get actually neutral lambda 0. This is actually hyperons, and this positive kaons. Okay. So this capture of photon by a proton is an example of electromagnetic interaction. Okay. Now, another important example is the radiative capture. Radiative capture. In fact, you can see here a neutron actually captures this gamma photon, and after capturing this gamma photon, we get a negatively charged pion and proton. Okay. So this radiative capture is also an important example of EM interaction. Okay. Now, the neutral particles pi 0 and sigma 0, both of these decay electromagnetically. It means decay of pi 0 and decay of sigma 0 takes place via electromagnetic interaction. You can see this pi 0 is actually decayed into two photons, gamma plus gamma, and this sigma 0, this is actually decayed into this lambda 0 hyperon and this gamma photon. Okay, so these two reactions also represent an electromagnetic interaction. Okay, now the decay of eta 0 into a photon also takes place, and that is also an example of EM interaction. So this eta 0 is also decayed into two photons, and this is an example of electromagnetic interaction. You have to remember these reactions. Okay. Now you have seen, just I have told you that during EM interaction, the isospin may remain conserved or may not remain conserved. You can see the rule of isospin during this EM interaction. When you say that this delta T is equal to 0, it means T, that is isospin, remains constant. But when you say that delta T is equal to plus minus 1, this is also permitted, then this T is not constant. It means isospin is not constant. So in EM interaction, you can say that the isospin may remain conserved or it may not remain conserved. So as in EM interaction, the conservation of isospin is not needed strictly. It may remain conserved or it may not remain conserved. So in this condition, the decay of this eta 0 is also possible in producing the 3 pi mesons. Sorry, the page has been turned, but don't be worried. This will be just okay in few seconds. You can see this is just okay. Okay. You can see I have told you that the decay of eta 0 into photon is an example of a what? EM interaction. But at the same time, since the conservation of isospin is not needed in EM interaction, so it is also possible that this eta 0 is decayed into 3 pi mesons, that is pi plus, pi minus and pi 0. And this is also an example of EM interaction. Now, when you know a particle and its antiparticle collide or interact with one another, then it is decayed into photon, and that process is called annihilation. Okay. For example, if you can see here, if there is an interaction between electron and its antiparticle E plus, that is positron, okay, then we get a gamma photon. You can see this diagram. This is actually Feynman diagram, you can also say. And this annihilation is also a very good example of this EM interaction. So you can say that the annihilation of particles and their antiparticles is a very good example of EM interaction. Okay. So these were some of the important examples of EM interaction, and you should remember these interactions, and this will be very helpful in your examination, because sometimes objective question will be asked, a reaction will be given, and you have to say that what type of interaction is taking place in this reaction. Okay. Now, I have mentioned here two important characteristic or two important properties of this EM interaction, that the characteristic lifetime of this interaction is 10 to the power minus 15 second, and its characteristic cross section is 10 to the power minus 4 millibarn. MB means millibarn. Barn. You know, barn is actually a very small unit of area. In fact, one barn is equal to what? This is 10 to the power minus 28 meter square. This is a very a small unit of area. Okay. So you have to remember these values. Characteristic lifetime of this interaction is 10 to the power minus 15 second. This is a very small time, and the characteristic cross section of this nuclear process is actually 10 to the power minus 14 millibar. Okay, so these were some of the important characteristics of the electromagnetic interaction, and as I have told you earlier that in the forthcoming lecture, in a single lecture we will discuss actually remaining two interactions. In only one lecture we will see the important characteristics of the weak interaction and the strong nuclear interaction. Okay, I think you have enjoyed this lecture, and this was a very short lecture, and but this is very informative, very important for you. So watch the video seriously, and if you like this lecture, you must write some comment in the comment box.